All right, this is this is the start of our AP prep, and it's what's considered Unit 1 on the College Board. This questions all come from College Board to help review each part of calculus. So the first part, calculus, is limits, derivatives, integration. And so the first part is understanding limits and continuity. So in number 1, the graph of a function shown above, which of the following is false when you look at the graph? Is the function continuous at A? It doesn't look that way. Is there a relative maximum at A? And there is. There's a high point at A. X equals A. Is it in the domain? And yes, there is a value for the domain in here, so there is a point there. The limit from the right and the limit from the left, do they equal each other? Yes. Does the limit exist at A? Yes, because as it's approaching the same y value. So the only one that's false here is A. So we're going to write down why that is. So there is a discontinuity when x equals a. There's a hole, and that means it's not continuous at x equals a. Question number 2. For x is greater than 0, the horizontal line y equals 2 is an asymptote for the graph of the function f. Which of the following statements must be true? So if y equals 2 is a horizontal, is an asymptote, that has to do with end behavior. So in this case, the right end behavior is going to 2. So if it has an asymptote here, what must be true? F at 0 equals 2. That does not need to be true. That f at x can't equal 2 for all of the x and so on. Also, horizontal asymptote doesn't mean it can't equal it. It just means end behavior. F at 2 is undefined. And again, it's the y value anyways. All right, the limit as x approaches 2 is infinity. And so which one is the true statement? The limit as x approaches infinity. That is the right end behavior. And so where is the right end going? To 2. That is the correct statement. Turn the page. Number 3. At x equals 3, the function given by f at x equals x squared and 6x subtract 9. And then it gives you a bunch of different options for this when x equals 3. So I'm first going to do this. I'm going to plug 3 in. And exactly there, it's going to equal this. So I could write it also as a limit. So the limit as x approaches 3, and I'd write it this way, from the left. So that means if you plug 3 into the top, the answer is 9. The limit as x approaches 3 from the right of f at x. So on the right, 6 times 3 is 18. Take away 9, which is 9. So they have the same value. The left and the right, they equal the same thing. Therefore, is it undefined? No. Is it continuous because they both equal 9? Yes. Differential but not continuous. We're definitely going to cross that one out. So we know there's continuity because they both equal the same y value. So it is continuous. So these say it's not continuous, not differentiable, not continuous. So this is continuous, but not differentiable, continuous, and differentiable. So how can I tell? So we know it's continuous. How can I tell if it's differentiable? So I'm going to take the derivative of what I see and do the same thing. So that's 2x, and that is 6. And I'm going to do the same work. I'm going to write it as a limit. So the limit as x approaches 3 from the left of the derivative. So that answer is 6. The limit as x approaches 3 from the right for the derivative. So be comfortable writing the limit. So again, there's no variable, so the answer is always 6. And so they have the same derivative. They have the same y coordinate, so it is continuous. It is differentiable because the right agrees with the left. And so therefore the answer is E. It's both continuous and differentiable. Number 4. The limit as x approaches a for f at x equals L, where L is a real number. Which of the following must be true? So as x approaches a, you have an answer, which is L. So f at a exists. That does not need to be true. So the limit can approach a value, but when you get there, it doesn't have to mean that it exists. It means that f at x is continuous if the limit exists. Nope. It does not need to be continuous. You can have a hole, and it's approaching the hole on both sides. F at x is defined at x equals a. That's the same thing here. That's no. F at a equals L. Again, that answer is no. There may not be exist, right? It might be a hole there. So the answer to number 4 is none of the above. So if the limit exists, there may not be a value there. There might be a hole there. So look at each one, and do you understand it's what it is as it is approaching? When you get there, it may equal that number or may not. There might be a hole. It doesn't matter at that point. So that answer to number 4 is none of the above. Number 5. In number 5, f at x equals, now that should say x squared minus 3x plus 2 9. So just tell yourself that's x squared, so that's a graphics issue, plus 9. And the second one is k times x plus 1 for greater than 2. And it says the function f is defined above. For what value of x is f continuous at x equals 2? So write that as a limit. So that's the limit as x approaches 2. Hello. From the left. All right, sweetheart. X squared subtract 3x plus 9. I want to know that answer. I want to know what the answer is to the right. So I write it as 2 limits. And then I put the answers equal to each other. And actually, I didn't even need to write this. I could have just written f at x in that spot. But anyways, you're going to plug in 2 for x. So if you do that, that is 4, take away 12. That's negative 8 plus 9, that's 1. Plug in 2. Wait, 4? I said 2, right? Let's try it again. Plug in 2, and you get 4 minus 6 plus 9 if you plug in 2. So that is positive 7. Plug in 2 for x, and you get 2k plus 1. We're then going to let them equal each other. So that's the definition of continuity. So the left side and the right side, those limits equal each other, and it's equal at the actual function there. So we're going to subtract 1, divide by 2, and you get the answer 3. Turn the page. And you have your answer. Number 6. If the limit as x approaches a of f at x equals f at a, so if the limit equals what the function value is, then which of the statements must be true? Must it be continuous? I think it might be. Must it be differentiable? No. So you could have a sharp corner or sharp turn. That would make it, it's still continuous, but it's not differentiable. C, for all values of x, f at x equals f at a. No. The line y equals f at a is a tangent to the graph of f at x equals a. No. The line x equals a is a vertical asymptote. That must be true? I don't see anything to do with an asymptote in the question. That is the calculus definition of continuity. The limit exists, and if you evaluate the function at that same number, they're equal to each other. Therefore, it's continuous. That is the definition of continuity. Number 7. The graph of a function of f is shown below, or shown above. Which of the following statements is true? F at a equals 2. It does not. F at a equals 1. F is continuous at a. That is not true. There's a hole there. The limit as x approaches a is 1. The limit here from the left and from the right is not 1. That's not what it's approaching. The limit as x approaches a from the left and the right is 2. Is that the y-coordinate it's approaching from the left and right? The answer is yes. And the last one is, does the limit doesn't exist? The limit does exist. It's approaching the same y value from the left and right. So from the left and from the right, the agree is the limit is equal to 2. The function value is equal to 1. So if they had the same value, then it would be continuous. Number 8. If f is a continuous function from a to b, which of the following must be true in terms of continuity? All right, let's see about these with continuity again. So look at each one. If the function is continuous, which one must be true? So 1, the derivative exists all the way through. Must that be true for continuity? And the answer is no. And the example is you could have a sharp corner. The derivative doesn't exist at that sharp turn, but it's still continuous. If f at x sub 0 is a maximum of f, then that means the derivative of that must be 0. No, because you could have a maximum at the ends necessarily, or it could be a minimum, right, in terms of that. So if that is a maximum, then so on. So the answer to that is no. The limit as x approaches 0 of f at x of this limit, and so on. Let me go back to that one. The derivative at x equals 0 for something between a and b. Must that be true if it's continuous? So no, you could be continuous from a to b, and there may not be any. This means there's a turning point. There may not be a turning point. The graph of f, the derivative, is a straight line. No, the graph doesn't have to be a straight line. That would be if it was a linear relationship. But just for continuity, no. So this understanding is the limit as x approaches a number is equal to that limit from the right and from the left. Anyway, this is a fancy definition where you have the limit equaling the limit. The subscript is a little bit off here. So to like understand it, so as x approaches x sub 0, and then as x approaches sub 0, so whatever this limit value is, if you plug it into the function, they're equal to each other. That's what it's saying. So if you know what the limit value is and you plug it into the function and they're equal to each other, that's a definition of continuity. All right, so the answer to 8 was C. Number 9. In number 9, you have a graph, and this is in the figure above. It shows the graph of a function. Which of the following are true? So the limit as x approaches 2 from the left. So here's 2. 2 from the left, the answer is -1, is equal to f at 2. So from the left, f at 2, that definitely seems like it's true. So I'm going to put a check mark there. So the first question has to do with that. How about the limit as x approaches 6 from the left? So as 6 is from the left, that's here, it's equal to the limit from 6 from the right. So the left and the right both agree on the y-coordinate. I agree with that. The limit as x approaches 6 is equal to f at 6. Well, the limit value is -1, but the actual value of the function is down here at -3. So I don't agree with 3, but I do agree with 1 and 2. So There's your answer. 1 and 2 only are the true statements. A. The graph of the function is shown above. For which of the following values does the limit as x approaches c f at x equals 1? So I'm looking for this, right? So the y coordinate is 1. That's what we're looking to approach. So if I look here, the y value at -2, the limit exists and it's approaching 1. And right here at 0, it's doing the same thing. Nowhere else does the limit exist. So when x equals -2, so as it's approaching -2, the limit is +1. As x is approaching 0, the y value is that as well. So I have two numbers where the limit would exist there. I have -2 and 0. So let's see if I have that answer. -2 and 0, and then you have your answer. Number 11. In number 11, let f be that function if the line y equals b is a horizontal asymptote to the graph of f, then what does b equal? So in other words, what is the horizontal asymptote that you see? And that has to do with end behavior, and that has to do with power terms. So if I think of the power term in the numerator, it'd be x times 2x, which is 2x squared. In the denominator, if you multiplied it out, it would be x squared. So that's power over power, and the horizontal asymptote would be at 2. That's what b would equal, and you have your answer. In number 12, the graph of the function shown above that I'm looking at says if the limit as x approaches b of f at x exists, and f is not continuous at b, then where? So something where the limit exists, but there's no continuity, where would that value be for x? All right. So where does the limit exist, but there's no function value? So I want you to look right here at 0. The limit exists, but they don't equal each other. It's not continuous. So there's a hole there, and the limit exists. At the asymptote, the limit doesn't exist. And when there's a jump, the limit doesn't exist. So right here is where the limit exists, and it is not continuous. So that's when x approaches 0. So it's when b is 0 where that happens. Number 12. That was number 12. Number 13. In number 13, if a function f is continuous for all of x, and if f has a relative maximum at -1, 4, and a relative minimum at 3, -2, which of the following statements must be true? So a function is continuous and has a relative maximum when x is -1 and a minimum when x is 3. The graph of f has an inflection point somewhere between -1 and 3. There does not need to be an inflection point. Cross that one out. That f at -1 equals 0, or the derivative at -1 equals 0. And the answer is the derivative could be undefined to create a relative maximum. So the derivative doesn't have to equal 0. The derivative could be undefined. My camera's flashing. I'm going to try to get it to stop. See if I get it to stop. All right. So it could be undefined. So you could have a sharp corner that creates a maximum. The graph of f has a horizontal asymptote. I see no information about the right end behavior here in terms of turning points. The graph of f has a horizontal tangent at x equals 3. And again, it could be undefined there. So at x equals 3, there is a minimum, and there could be a horizontal tangent there that creates a turning point, but it could also be undefined. So there doesn't have to be a horizontal tangent there. It could simply be a sharp corner that creates a maximum. And then it says the graph of f intersects both axes. Can we graph that? So, I want to draw a graph. Where's negative 1 and 4? Where's 3 and negative 2? And what they said was, it's continuous. So if that's true, and this is continuous, remember negative 1, 4 is a maximum, and this is a minimum. So it could be a sharp corner on both sides. But the question is, if this is continuous, would it cross both axes to get from this point to this point without lifting up your pen? And the answer is yes. So the answer to number 13 is E. 14. Let f be a function that is continuous on a closed interval 1 to 3, with f at 1 equaling 10 and f at 3 equal 18. Which of the following statements must be true? Let's look at the options here. Sure, again, so again, just so I can write down, f at 1 equals 10. F at 3 equals 18. So if I graph that, you kind of look like that. So f at 1 is 10, f at 3 is 18. Which of the following must be true? Okay. So that's all I know. So it says f at 2 must be between 10 and 18. And so must it be between 10 and 18, or could it be lower than that? There's no information on that. So definitely A is not a must. F is increasing from 1 to 3. Well, could it decrease and then increase? So it's not only increasing. F at x equals 17 has at least one solution in the interval from 1 to 3. So one solution means there's just a y value. So from 17 is in between here, 10 and 18. So if this is continuous, however it's continuous, is there a y value at 17? Is there an x value for that? And because 17 is in between here, this is the intermediate theorem, the answer is yes. There has to be an answer. How about the derivative of x has to equal 8? No. How about the integration from 1 to 3 must be bigger than 20? So the area under the curve must be bigger than 20. So the only one that makes sense here is that there must be an answer, at least one answer of 17, because it's in the middle of the interval between 10 and 18 if it's continuous. Number 15. You're given a table of values. The table above shows selected values of a continuous function from 0 to 13. What is the fewest possible number of times f at x can equal 4? So look at how many times we cross over. So from 3 to 4.5, that's once. From 4.5 back down to 3, that's 2. 3 to 2.5 or 2.5 to 4.4, again we cross 4. So every time you cross over 4 in the interval, it's a possibility. So how many times did that happen? So the answer is 3 if it's continuous. Number 16. Let g be a continuous function on the closed interval from 0 to 1. G at 0 equals 1. I'm going to graph it. G at 0 equals 1. And G at 1 equals 0. Which of the following is not necessarily true? So that's what I have. I'm going to put that over here too, just so I can see it. and remember it. So that's all I know right now from 0 to 1. And it says, let's look at each possibility. So A says there exists a number from 0 to 1 so that g at h is greater than g at x for all of x from 0 to 1. So there is nothing there that says that must be true. For all of A and B from 0 to 1, if A equals B, then g at A equals g at B. So there's nothing also for that for all A and B from 0 to 1, if A equals B, then g at A has to equal g at B. There's nothing there that says that at all. There exists a number from 0 to 1 so that g at h equals a half. If this is continuous, right, between here, there exists a number between 0 and 1 such that g at h equals 3 over 2. And again, the question is, which of the following conditions... No, where is it? Make sure I got the right answer here. Which of the following statements must be true? No? What am I looking at here? For number 14, why am I not looking at it? I'm looking at number 16. Make sure here. Oh, there it is. Which of the following is not necessarily true? So that is true. 3 over 2, that is not a main interval. That's 1.5. And the greatest y value goes from 0 to 1. So this is the one they're looking for. This one does not necessarily enter. It could go up or down, but it doesn't have to. Other ones could be. And then for all of h in the open interval, the limit in terms of that, it may or may not be. That's the one they're looking for. Number 17. A student attempted to confirm that a function defined is continuous at 4. In which step does an error appear first? So to know if it's continuous at 4, so first of all, they factored out. Did they factor it out correctly? Yes. And then they removed a discontinuity. So at this step, when they removed a discontinuity, are they showing that it is continuous when they remove that discontinuity? So I'm worried about step number 2. Because f at 4 does not equal 3 over 2. There's a hole there. So you can remove it. So here we remove the discontinuity. The limit exists. That answer is 3 over 2. But it is the function value doesn't exist because you removed x minus 4. There's a hole there. So this is where the mistake was made at step number 3. If it was continuous, then the limit value and the function value would be exactly the same. Number 18. This is a calculator question, so I'm going to use a calculator. So the question is, for f at x, let f be the function defined above. Which of the following condition explains why f is not continuous at 2? So first of all, does the limit exist at 2? So I'm going to type it in and see if the limit exists at 2. Can you take out your calculator with me and see if it exists? So how do I do a limit with a calculator again? So let me clear this. So press menu, calculus, and limit. So that's number 4. And then it's the limit as x approaches 2. And then inside the function, we type in, go control, divide, and then type it in. So it's x cubed plus 2x, subtract 12. And then the denominator is 8 cosine pi over 2 . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . x, move the parentheses, plus 2x squared. So just double check that I typed it in correctly. So again, x cubed plus 2x subtract 12, 8 cosine pi over 2x plus 2x squared. All right, so that answer, the limit, is 7 over 4. Now, does f at 2 exist for that same one? So this is what I'm going to do to evaluate the function, is I'm going to highlight this part on the inside here. Oops. You know what? I'm just going to do this. So I want to edit it, so I'm going to do this. Okay, so if I wanted to evaluate it, I could type it in again. So x cubed plus 2x subtract 12, 8 cosine pi over 12, or pi over 2, x, plus 2x squared. So make sure I typed it in correctly. Then I'm going to go control equals into the vertical line, and then I'm going to type in x equals 2. And so when I type in x equals 2 here, the limit exists, but the value of the function is undefined. So that's what we're looking for. The limit exists, but the value of the function is undefined, so therefore it's not continuous. So which one says that? So this one says the limit or f at 2, it doesn't exist. That's not it. The limit exists, but f at 2 doesn't exist. That one's the one I'm looking for. Both the limit and f at 2 exist. Wrong. Both the limit and f at 2 exist. Wrong. So the only one that says the limit exists, but f at 2 doesn't exist, is the correct answer. And that's why it's not continuous. Look at number 19. So if it has a little calculator symbol, we'll use a calculator. Let f be this piecewise function defined above. Which of the following statements is false? So if this was continuous, then if I plug in 1 for each one of these. So if I plug in 1 here, then the answer is 5. That's the answer is 5. Plug in 1, it's 5. So this one is good. F is continuous at 2. So that involves, yes, it's in the middle of something that's continuous. So that's true. Number 3, x equals 3. So if I plug 3 here, I get negative 12 plus 9, 4. Definitely not continuous. So they don't all equal. So when you use 3 here, you get different answers for the y value. And is it continuous at 4? It is, because x subtract 6 is a continuous function, and it's not a piece where it breaks off there. So the right answer to C is, which of the following is false? And the answer is C. Number 20. The function g is defined by g at x equaling that. At what values of x does the graph of g have a vertical asymptote? So when you look at the denominator, which one would give you something that is undefined? So when you look here, if you factor this out, it's x subtract 5 and x plus 2. So the x subtract 5s you're going to remove. So it's going to create a hole there, not a vertical asymptote. When you look at this denominator, factor it out, you have x squared, x plus 3. The numerator is x plus 3, x plus 3. So which one creates a... factor out x squared, x plus 3, x plus 3. And then the question is, which one creates a vertical asymptote, something that's undefined in terms of it? Now, we can see that at x equals 0, there's going to be a vertical asymptote. But I can also see that x plus 3 gets removed. And so that removable thing then would create a hole All right, so let's turn the page. And the answer here is at 0. That's the one that's non-removable from the denominator. 21. The values of f at x So the values of f at x of a function can be arbitrarily large by taking x sufficiently close to 1 but not equal to 1. Which of the following must be true? So the values of f at x of a function can be made arbitrarily large by taking x sufficiently close to 1 but not equal to 1. Which one must be true then? So if it's arbitrarily large, it's saying as you approach 1, the answer is arbitrarily large. So which one describes that situation? As x approaches 1, the answer is arbitrarily large. So as x approaches 1, the function can be made arbitrarily large by taking x sufficiently close to 1, but not equal to 1. So this is the answer here. So it gets larger and larger and larger as x approaches 1, but not equal to 1 because it wouldn't exist then. 22. The function f is continuous at x equals 3. Which of the following must be true? So if this is true, think of the definition of continuity again. My camera's doing that again. See if I can settle my camera down just a little bit so it doesn't blink in and out and in and out. So this is the definition of continuity. The function value, the limit exists, and it's equal to the function value. That is the calculus definition of what continuity is. So at 3, the limit exists, and it's equal to the function value. Therefore, it is continuous. Number 23. Can you find the limit as x approaches infinity? This is a right-hand behavior question. So all we need is the power term over the power term. Divide out the x cubes, and where is the right-hand behavior going? And the answer is C, 1/4. That's like pre-calculus, right? Pretty cool. Did that. Number 24. For which of the following does the limit x approaches 4, for which of the following does the limit exist? So does it exist here at 4? Yes. The left and right agree. The point above doesn't matter. Does it exist here? Does the left side and right side both agree what the y value is? Yes. How about for number 4, this one? Does the limit exist at 4? Does the left side agree with the right side? No. So which is the only two that work? Is 1 and 2. So the answer is D. That's where it is. 25. Again, I'm going to try to get this camera to not keep blinking. There's something with light that's happening. I don't quite understand it. 25. It's probably the camera. What's the limit as x approaches 2 of this function? Can you evaluate a limit? And so the answer is, first, if you do a substitution, you're going to be indeterminate. So you actually already have skill to do if it's indeterminate. So if I look at the numerator, what's the answer? If I look at the denominator, what's the answer? So plug in 2, you get 4 plus 2 is 6, take away 6. So this is indeterminate. So what's one direction you can go when it's indeterminate? is you can use L'Hopital's rule. You could also factor and simplify. So L'Hopital's rule, take the derivative and then plug in again. Now that's pretty simple. So when you evaluate now, you get 5 over 4 and you get your answer. Now you could also algebraically factor and eliminate that way and remove something, but you can also use L'Hopital's rule because you know how to take derivatives and you know L'Hopital's rule. 26. Oh, I passed 26. 26 is at the bottom. So for number 26, find the limit as x approaches. So whenever I see a fraction, I'm going to separate it into two limits, the top and the bottom, and see what the answer is. So the limit for the numerator here is 0. The limit here, when I plug in 3, is 9. Take away 9. Did I write right? Take away 6. Take away 15. So that's not 0. I just want to make sure that I got that right. That's not 0, right? For number 26. 9 take away 6. So it says 0. So 9 take away 6 is 3. Take away, I get negative 12. So if I divide it, I get the answer 0 for number 26. Did I wrote it down wrong? So as it's approaching 3. Oh, did I do 3? Wrong. 9 take away 6 take away 15, or 9 take away 9. Doesn't it? Don't you get that? All right, let's see also here. I know if you factor it, it's x plus 3, x subtract 3. This is x subtract 5 and x plus 3. So when you plug in 3, I still get the answer 0. Maybe it's an answer over here. Oopsie. Oh, there's an answer 0. Perfect. $27. Stop blinking. So you can use L'Hopital's rule, but for that one's not L'Hopital. It wasn't indeterminate. It was 0 divided by a number. Okay. Number 27. Sometimes I gotta like figure it out two different ways just to make sure everything's okay. All right. For f at x, it equals ln x, and then x squared ln 2. Then what's the limit as x approaches 2? So for that to be true, the left side for ln x would equal ln 2. The right for that if I plug in, I get 4 ln 2. They don't equal each other. So the left does not equal the right. I get ln 2 here. Then when I plug in 2 here, I get 4 ln 2. Definitely not the same number. So because the left side does not agree with the right side, the limit does not exist. Mean Girls. Here we go. Do you know the movie? 28. For 28, the graph of the function is shown above. Which of the following statements must be false? Don't know. Sometimes for some this camera's has a mind of its own. I'm going to try to like work on the lighting in the room. Maybe the lighting's bothering it. All right, let's see if that helps. Just kind of get the lighting more consistent. Doesn't like the light coming in. All right, the graph above, what's true? F at A. Does F at A exist? Yes. It's right there at that point. F at x is defined from 0 to a. Yes. F is not continuous at a. That's true. There's a hole there. The limit as x approaches a exists. Yes. The derivative as x approaches a, the derivative exists at a. Nope. So the one that's false here, the derivative does not exist when it's not continuous. So you can't have the derivative of a value that is not continuous. So when x equals a, there is no derivative there. But everything else is true. 29. The function f is defined above where c is a constant. For what value of c is f continuous when x equals 0? So we're looking for from the left and the right in continuity. So the left and right is this. Oops. Let's try this again. The limit as x approaches 0 for f at x equals, and it's not what it is when it gets there, so it's the above one. So plug in 0 there. And so it's sine 0 over this. Now the value of sine at the angle 0 is 0. So for this to be continuous, c would also have to equal 0. So they would have the same value. So you kind of have to know your unit circle, that when you plug in 0, the answer is 0. Oh, wait a second. Let me look at it again. So when I look at the limit at 0, it's actually indeterminate. So what do you do when it's indeterminate? Is you're going to do L'Hopital's rule when it's indeterminate. So L'Hopital's rule, the derivative of sine is cosine 5x times 5, so there's a hook there. And the derivative of 8x is 8. So now when I plug in 0, cosine at 0 is actually equal to 1. That's the x coordinate at the angle 0. So it becomes 5 over 8. Way better. So number 29, the answer is 5 over 8. Number 30. F at x equals x squared plus b squared, b at x, bx plus 2b. Let f be the function defined above, whereas b is a constant. For what values of b is f continuous? So that would mean the left side would have to equal the right side. So for the left, plug in 2, you get 4 plus b squared. For the right limit, you get 2b plus 2b, or not to be, and then you'd make them equal to each other. So 4 plus b squared is equal to 2b plus 2b, and then you would solve it. So I have b squared, subtract 4b, plus 4, factor this. So the two numbers that multiply to 4 and add to negative 4. So the answer here is positive 2 is what solves it. So when b equals 2, it's continuous. If b equals 0, it would not be continuous. I just have the answer key, so I'm always double checking to make sure that I'm doing it correctly with you. Number 31. In number 31, again, you're asked if a is a constant, for what values is it continuous? So we're going to write it as a limit as x approaches 3 from the left of f at x. So for that answer, you would plug in 3 and you would have a squared plus 3 squared. the limit as x approaches 3 from the right for f at x. Again, plug in 3 and you get 6a. So I have a squared plus 9 equals 6a. Subtract 6a. Factor it. And you have your answer. So in this situation, when a equals 3, it would be continuous. (32) If f is the function for f at x equals x squared subtract 9, x squared plus 2x subtract 15, then the limit of f at x as x approaches 3 is what? Now, when I do this as a limit from the left, oh sorry, not the left, the numerator. So if I plug in 3 into the numerator, I don't want to write 0 over 0. Oops. So this is not the left and the right, just separating the numerator and the denominator. Notice this one, you get 9 plus 6, that's 15, take away 15. It is indeterminate, so I can use L'Hopital's rule. So the limit as x approaches 3 of f at x, you can take the derivatives, that's 2x, and the derivative, which is 2x plus 2, and then you plug in. So if you plug in here, you get the answer 6 over 8. That's 3/4. Number 33. So g at x equals 2 cosine squared x subtract 1. Cosine x subtract sine x. So the limit as x approaches pi over 4. So the limit as x approaches pi over 4 for the numerator, what would it equal? So when I plug pi over 4 in for cosine, that's root 2 over 2. And I'm going to square it minus 1. So if I simplify it, this would be 2 over 4, but this would actually be 4 divided by 4. So 2 times a half, take away 1, that answer is going to be 0. If I do the same thing to the denominator, that's cosine x subtract sine x. Again, at pi over 4, it's root 2 over 2. Both of them are root 2 over 2, so it is indeterminate. So now we can do L'Hopital's rule by taking the derivative of g at x. So the derivative of the top, think of that as squared. So 2 times 2. So 2 times 2 is 4. Subtract 1 to the exponent, and then the derivative of cosine is negative sine. That's going to be the hook. The derivative of negative 1 is 0. The derivative of cosine is negative sine. And the derivative of sine is cosine, but it stays negative. And now we're going to do the same thing. Sorry, no equal sign there. That's what it should look like. You don't need g at x. No, just put it into the limit. Now plug in pi over 4. And you get, wow, which one do you get? Is equivalent to which of the following? So do any of these match in terms of that? So the answer here is root 2 over 2 plus root 2 over 2. It's obviously not equal to the numerator or denominator, or this, because that's that. So you can use process of elimination and know none of those are true in terms of the limit value. So B is the only one it could be, because all of this is not true. That answer is 0 and 0, and that's indeterminate. That's 0 over 0. So this is the one that could be true. So if I did the work here, cosine of pi over 4 is root 2 over 2. And then negative root 2 over 2. Here we have negative root 2 over 2 and negative root 2 over 2. All right. So if I put this together, the denominator is 2 negative 2 root 2 over 2. Which then crosses out with one of the root 2's in the numerator. They cross out. And then negative 2 goes into 4 negative 2 times. So that leaves me root 2 over 2. They cross out and I just get root 2. All right. Perhaps if I simplified this, I'd have a better sense of it where they could be equivalent. Well, root 2 over 2 plus root 2 over 2 is 2 root 2 over 2. So the 2's divide out. So I do get the same answer. So the answer I get here is root 2. The answer I get here is root 2. So it does give you the same answer by doing L'Hopital's rule that way. I was trying to think if you could use a trig identity, but that's good right there. All right, number 34. In number 34, it is known that the limit as x approaches 0 of sine 2x over 2x equals 1. What is the limit as x approaches 0 for this tangent 2x over 6x secant 3x? So again, if I plug in 0, I'm going to get indeterminate. So I could take the derivative and plug in 0 again to see what the answer is. So in doing the product rule, I can factor out, oops, this should be 3x in here. And that's 2x. Nothing's going to simplify. It's going to get, so if I take the derivative and then plug in 0, so if I plug in 0 for x, all of that's going to eliminate. If I plug in 0, the value of secant at 0 is 1. So I would get the answer 6. The value of secant at 0 is 1, so I get 1 times 2, which is 2. So I get a third by doing L'Hopital's rule. Take the derivative and the derivative, use the product rule, and you have the answer. Done. Number 35. The graph of the function f is shown above. What is the limit as x approaches negative 1? Really? The y coordinate, which is 2. Oh, for that. And then you plug, so for the limit question, inside the answer is 2. And then f at 2, the answer would be, I think, 2. Let's see if that's true or not. So it's kind of an inside-out thing. Oh, it's the left-hand behavior. Okay. So inside out, the limit as x approaches negative 1 from the inside of the function, the answer is 2. And then because of that, it's the left-hand limit that we're looking at, and so the answer is 5 for the left-hand limit. So from the left, the answer is 2. So then from the left, the answer is 5, because they agree like that. So the answer is that. All right. Let f be a piecewise function as defined above. The value of x is 2 from the right. What is the answer? So 2 from the right would be here, and you would plug 2 in, and I get the answer 11. Make sure that's right. And we're good. Number 37, f at 2 equals 3, g at 2 equals negative 6, h at 2 equals negative 3. The table above shows selected values and limits of the function for f, g, and h. What is the limit as x approaches 2, and then you plug in the values that you see? So for h at x, the limit is 2. For f at x, it's 4. For g at x, the limit as it approaches 2 is negative 6. I believe that's how you're going to answer it. Let's just double check, and then you simplify it. So the answer would be 20 take away 6, so it's 2 times 14, which is 28. That's what I believe the answer would be. So just looking at the limit values and plugging them into an algebra, and the answer is 28. Number 38, the graph of the function f is shown above. Which of the following statements is true? I'm gonna have to go flippity flip here. So first of all, is it f is discontinuous at 0 because the limit doesn't exist. Does the limit exist at 0? Yes. So that one's wrong. F is not continuous at 3 because the limit doesn't equal f at 3. That's why it's not continuous. Let's see. So at 3, the limit does not equal the value, therefore it's not continuous. That looks pretty good to me. Just checking the answer key quick. So f is discontinuous at x equals 3 because the limit doesn't equal. So the limit value is 0. The actual value of the function is 2 because they don't agree. The second one says f is not continuous at 5 because the limit as x approaches 5 from the left doesn't exist. So as x approaches 5 from the left, it does exist. The answer is 4. So the correct answer is B. So it's not continuous because the limit value as x approaches 3 doesn't equal f at 3, and that's the calculus definition of continuity. Number 39. So you're given a graph. And it says the size of a population of fish is modeled by this function p at t. That's the number of fish. And t gives the number of years after the first introduction from 0 to 10. The graph of the function p and the line tangent p at t equals 4 is shown. Which of the following gives the best estimate for the instantaneous rate of change at 4? So I want to know what the value of that slope is. Which one would give me the best estimate of that? So if you just go p at 4, that would give you the slope. No, it would not. That's just the function value there. The slope between 0 and 4 would not be a great estimate. The slope between 0 and 8 would not be a good estimate. Those are too very far apart. The slope between 3.9 and 4.1, would that be a good estimate at 4? And the answer is yes. This one would give you the best estimate for the slope of the tangent line because it's the values closest to 4. So if you find the slope between 3.9 and 4.1, that would be the best estimate. So I'm going to get a similar question here. The size of bacteria, and you have a graph and want to know what's the slope, the instantaneous rate of change is the slope of this line, what would give you the best estimate of that? So we're looking at the same idea here, that the slope between 7.9 and 8.1 would give you the best estimate of what that slope would be. Look at number 41. In number 41, an automobile is driven on a straight road, and the distance traveled by the automobile after time t equals 0 is given by a quadratic function s, where s at t is measured in feet and measured in seconds from 0 to 12. Of the following, which gives the best estimate of the velocity of the automobile in feet per second? So the distance is the same as position. So the position is a quadratic. So velocity is the derivative of that. So if this is a quadratic, any quadratic, the derivative of that is going to be linear, right? So which of the following gives the best estimate of the velocity of it? And again, we're talking about the difference quotient for position. So first of all, it would be linear, but also if you take the position, you're trying to find 2 points that are close to 8. So if you find the slope around 8, you're taking 2 points that are close to 8. So this is the one between 9 and 7 that surround 8. This would be the slope formula, y2 minus y1, x2 minus x1, which would give you the best estimate for the slope there. Number 42. For number 42, h is a piecewise linear function, so that the limit as x approaches 3 doesn't exist. Which of the following could be representative of the function? So does the limit exist here? So 12 take away 3 is 9. 4 times 3 is 12. Take away 3 is 9. So that seems okay. This one, as x approaches 3 from the left and from the right, is it the right answer? Is it 0? Does the limit exist? Maybe. We don't know from that table of values. Here, does the limit exist at 3? From the left and from the right, the limit does not exist for that table. So which one would the limit could be in terms of it? So the answer, which one could be representation of it, does not exist. So number 1, it does exist. For these, it may not exist. This one definitely doesn't exist. For the table of values, it may not exist. And for this, it definitely doesn't exist. So the answer is 2 and 3. It may not exist. I have to be a good reader doing this. Number 43. Let f be a function defined by that. Which of the following is a horizontal asymptote of the graph? So it's power term over power term. So if I look at that, I want you to notice 3 to the x and e to the 2x. Very similar power situation, right? Now 3 to the x is a little bit more powerful than e to it, but they're very close because e is 2.7 to it and then 3. But if you notice e to the 2x plus 1, as you put in numbers for x, because of the 2 times x here, I want you to notice that it's going to increase faster in the bottom. Now, one of the ways we could tell this is also taking the derivative. So if I take the derivative of the top and the bottom, which one is going to be increasing faster in terms of it? And it's close, but the denominator is going to be increasing faster than the numerator, especially because of the ln 3 times 3x. Ln 3 is smaller. E to the 2x is going to increase a little bit faster. So if the bottom is increasing faster, then the horizontal asymptote is 0. All right, let f be a function there. Which of the following is a horizontal asymptote? This is power term over power term. So look carefully. The numerator is negative 7x to the fourth. The denominator, the power term, is x to the fourth. So I get the answer negative 7. Let me make sure that's good. And it is. Turn the page. We're almost done. These are some easier questions, I think, at the end. The graph of the function shown above, what's the limit as x approaches 4? So look at this graph. Look at 4. What's the limit as x approaches 4? Does the left side equal the right side? No way. So for number 45, the limit does not exist. Next page. I know some of these questions are just too large from College Board, but I have to show you some graphs. What's the limit as x approaches 2 from the right? So from the right, what's the y value from the right? And the answer is positive 1. (47). You're given a table. Above gives values of a function at selected values of x. Which of the following conclusions is supported by the data in the table? So what do you notice about it? First, before I turn the page, what do you notice about the data here? So as it's getting closer to 2, does the limit exist there at 2? So from the left and from the right, do they agree what the answer is? So from the left, the answer looks like it's negative 1 as it approaches 2. From the right, the answer looks like it's approaching 6. So the limit as x approaches 2 doesn't exist because they don't agree. The limit from the left is negative 1 and from the right is positive 6. That's the one I was saying. There's your answer. All right, number 48. The table above gives values of which of the following conclusions can be made. So let's look at the x values. This is getting closer to 11 and to 11. Are they both approaching the same y value? It looks like they're both approaching 32. So if I look at the answer, as x approaches 11, the answer is 32. Let me double check. That's what it looks like what the answer is. So can you read table of values to evaluate a limit? So as x approaches 11, that's the answer. From the right and from the left, they both seem to agree what the answer is. 49. You're given a graph. The graph of the function f is shown above. Which of the following could be a table of values for f that could describe it? So I want you to look that at 1, the answer is 7. So if 1 is the answer 7, then already C and D are wrong. And then what's the difference between A and B? So at the answer 1, the answer is 7. So what is the differences? So here, when it's close to 1, the answer is almost 7. So at 1, is the answer almost 7? So from the left, the answer is just a bit more than 4. That's what this is, right? So this one's wrong. So looking off the graph and understanding limits, you can see the answer. Number 50. So which one could match this graph? So I see the limit here. The value at negative 1 is 2, and the limit is 3. So the value at negative 1 is 2. So which ones will I cross out then, if that's true? So the value at negative 1 is 2. So C is wrong and D is wrong. So -1 is 2. And then which one shows the correct one? So they're the same, they're the same. This is a difference here. So as x is approaching -1 from the left, is the answer 2 or is the answer closer to 3? So -1 from the left, the answer right here is closer to 3 rather than 2. So the one that's closer to 3 is the answer for B. And you have your answer. All right, we're almost there. All right, turn the page. 3 more questions. So for 51, let f be a function defined for all real numbers. Which is the best interpretation of this? The limit as x approaches 2 is equal to 7. Which is the first one? I have 3 questions left on a video that I need to do. Okay?
No, I didn't tell Joshua. I said,
You can go over there.
Come in here and be quiet. I did not
Please?
tell him that we're going to...
All right, thank you. I'll talk to you soon. I promise. Thank you. So the value of the function of f at x equals 2 is 7. No, it's the limit, doesn't have to equal that. The value of the function of f at x equals 7 is 2. No. As x approaches 2, the function approaches 7. Yes, that is the definition of a limit right there. So the answer to number 51, or right there, is that one, part C. As x approaches 2, the values of f at x approach 7. So the answer is C. Let's see if I can get it focused in there. There we go. All right, number 52. It says, let f be a function defined. Which is the best interpretation of that limit? The limit as x approaches 3 equals 5. It is not the value. It's not A. It's not B. As x approaches 3, the function approaches 5. That's exactly the correct interpretation of it. All right, one more left, number 53, and then the first unit from College Board would be done to review. So the big ideas were limits and continuity, and we did some other tools, calculus tools as well. The graph of the function f is shown above. What's the value of the limit as x approaches 0 of this function, 1 minus x squared? So when I look here, I would substitute 0 in. And what's the value as x approaches 0? So x approaches 0, this right here. Let's see if I can have the correct understanding of it. So what's the limit as x approaches 0 using this function inside? So as x approaches 0, I get the answer as it approaches 1. So when I look at that, in terms of the understanding of the graph, how would I understand the interpretation of a limit written like that? So I'm looking on the answer key to make sure I can try to understand it correctly. So 1 subtract x squared. The limit as x approaches 0. So if it was f at x, in terms of what we're looking at, then that answer would be 2. So make it equal to 1 subtract x squared, add x squared, for what value would that be true? I'm not getting the answer I'm looking for. So the limit as x approaches 0 here. The y value is 2. But I have 1 subtract x squared. Maybe this. Try it this way. Limit as x approaches 0. And if I separate it in terms of 1 and separate it in terms of x squared, in terms of looking off the view, because the limit here would be 2. Maybe the answer then would be 1 minus in terms of 2 squared. All right. I'm actually a little bit, I got to think it through. But the answer on the answer key is 3. So I need to figure out algebraically, and I'm looking on the answer key, and they're not showing me any steps to know how they got the answer 3, to understand estimating limit values from the graph in terms of what they did in this. So you have a situation where you're looking off the graph of f, 1 minus x squared as x approaches 0. So as x approaches 0 for f at x, the answer is 2. And so if I plug that in, how would that answer there be 3? So if I worked backwards and try to understand it, what would it be? All right. Well, I'm going to let it go right now. So the answer is 3. I'll look at it in terms of that and try to understand it. I know the limit as x approaches 2, 0 is 2, and then try to interpret it in terms of 1 minus x squared. So the limit, try one more time, as x approaches 0 of f at x, that answer is 2. So if it's the limit as x approaches 0 of f at 1 minus x squared, what would that answer then give you? And try to get an understanding of it. All right, I have to think it through, but they said the answer is 3. All right, Mr. G Math over and out. Until next time.